Imagine you are parking your car in a standard multi-story concrete garage. It feels solid, permanent, indestructible. You park next to a sleek, modern electric vehicle and walk away. But deep inside that vehicle's battery pack, a single cell shorts out. Within milliseconds, a chemical chain reaction begins that cannot be stopped. This isn't a normal car fire. It doesn't burn, it explodes with the ferocity of a jet engine, releasing heat so intense it doesn't just scorch the paint. It begins to liquefy the very structure of the building itself. Firefighters call this thermal runaway. Structural engineers call it a nightmare scenario. We are rapidly filling 50-year-old parking structures with 21st century technology that burns hotter, faster, and longer than anything they were designed to withstand. We aren't just parking cars, we are parking thousands of potential chemical bombs inside skeletons of concrete that may be one spark away from catastrophic failure. This is the mega defect of the Green Revolution, the terrifying reality that electric cars might be capable of bringing down your parking garage, just as our physical infrastructure struggles to keep up with new technology. Our digital infrastructure often lags behind the threats targeting it. You wouldn't park your car in a collapsing building, so don't leave your personal data exposed on an unsecured network. Protecting your digital life is essential. That's why I use NordVPN. NordVPN builds an encrypted tunnel for your data, shielding you from hackers and surveillance. It's the structural reinforcement your online life needs. Plus, it lets you bypass geo-restrictions with a single click. Secure your digital foundation today and use code MEGA DEFECT for up to 73% off plus 3 extra months. To understand the threat, we first have to understand the fire itself. A traditional internal combustion engine vehicle fire involves gasoline. Gasoline is flammable, certainly, but it requires oxygen from the air to burn. It burns largely on the surface, and while dangerous, its behavior is predictable. Firefighters have spent 100 years perfecting the methods to extinguish it. Cut the oxygen, cool the fuel, and the fire dies. An electric vehicle battery fire is fundamentally different. It is not a fire in the traditional sense. It is a chemical decomposition event known as thermal runaway. A lithium-ion battery pack consists of thousands of individual cells. If one cell is damaged by a manufacturing defect, a software glitch, or a physical impact, it begins to heat up uncontrollably. The heat breaks down the separator between the anode and the cathode, causing an internal short circuit. This releases oxygen inside the battery cell itself. This is the crucial, terrifying difference. An EV fire generates its own oxygen. You cannot smother it. You can dump a mountain of sand on it. You can submerge it in water, but the chemical reaction will continue to rage until the fuel is exhausted. It burns with a directed blowtorch-like intensity that consumes everything in its path. While a gas car fire might peak at around 1,500 degrees Fahrenheit, a lithium-ion battery fire can easily exceed 5,000 degrees Fahrenheit in localized spots. This isn't just a hotter fire, it is a completely different species of energy release, one that our current firefighting tactics are woefully ill-equipped to handle. Now let's look at the cage we are putting this beast into: the concrete parking garage. We tend to think of concrete as invincible, a stone material that cannot burn. And while concrete itself doesn't ignite, it has a fatal weakness: extreme heat. Concrete is a composite material made of cement, aggregate, and water. It gets its tensile strength, the ability to hold up floors, without snapping, from steel rebar buried deep inside it. When concrete is exposed to the rapid extreme temperature spike of an EV fire, a phenomenon called explosive spalling can occur. The moisture trapped inside the concrete instantly turns to steam. Because the heat rise is so fast, faster than a traditional fire, the steam cannot escape through the pores of the concrete. The internal pressure builds until the concrete literally explodes from the inside out, popping off in chunks and layers. This spalling exposes the steel rebar directly to the 5,000-degree inferno. Steel begins to lose its structural strength at around 600 degrees Fahrenheit. By 1,100 degrees, it has lost 50% of its load-bearing capacity. In an EV fire, the rebar can be heated to points where it becomes as soft as spaghetti. In a pre-stressed concrete floor, the type used in almost every modern parking garage, the steel cables are pulled incredibly tight to hold the floor up. If those cables are heated and lose their tension, the floor doesn't just sag, it snaps. The building was designed to withstand a gas fire for a few hours. It was never engineered to survive a chemical blowtorch. The systemic mega defect here is a massive gap in regulation. The vast majority of parking structures in the United States and Europe were built decades ago, designed under building codes from the 1970s, 80s, and 90s. These codes calculated fire load based on vehicles with plastic interiors and gas tanks. They assumed a certain rate of heat release in a certain duration of fire. They assumed that a sprinkler system could control the spread. Modern electric vehicles are significantly heavier than their gas counterparts, often weighing 30% to 50% more due to the battery packs. We are filling these old garages with vehicles that are physically heavier, stressing the structural load limits even before a fire starts. Then we introduce a fire load that burns longer and hotter. Current building codes generally do not require structural fireproofing in open parking garages because the assumption was that heat would dissipate into the open air. That assumption works for a gas fire. It does not work for a battery fire that releases heat energy at a rate that overwhelms the dissipation capacity of the structure. We are operating under a regulatory hallucination, pretending that swapping the engine type doesn't fundamentally change the physics of the environment. In a typical garage fire scenario, the sprinkler system activates to cool the surrounding area and prevent the fire from spreading to adjacent cars. But standard sprinkler systems are utterly ineffective against a lithium-ion battery and thermal runaway. The water simply bounces off the casing or evaporates instantly upon contact with the intense heat. To extinguish an EV fire, firefighters often need to use 20,000 to 30,000 gallons of water, more than 10 times what is needed for a gas car. In a parking garage, there is no access to that volume of water. Fire trucks cannot fit inside low-clearance structures. Hoses have to be run manually up stairwells. And even if they could get the water there, where does it go? Parking garages are not designed with drainage systems capable of handling 30,000 gallons of hazardous, chemically contaminated runoff. The water weight alone adds an immense live load to a structure that might already be compromised by heat. Furthermore, because the fire generates its own oxygen, it can reignite hours or even days later. A fire crew might think they have extinguished the blaze only for it to flare up again with renewed intensity after they have left, threatening the weakened structure all over again. The ultimate nightmare scenario that keeps structural engineers awake at night is progressive collapse. We saw a preview of this risk in the Liverpool King's Dock car park fire in 2017. That was a fire involving internal combustion engines, yet it burned so hot and spread so fast that it destroyed 1,400 vehicles and melted the concrete floor slabs, compromising the entire structure. Now imagine that scenario with EVs. One car enters thermal runaway. The intense directed jet of flame ignites the battery pack of the EV parked next to it. Unlike gas tanks, which rarely explode, battery packs are highly susceptible to chain reactions. You get a domino effect of thermal runaway events. The heat release rate grows exponentially. The concrete ceiling above the fire begins to spall. The internal tension cables snap. The floor slab, unable to support the heavy weight of the EVs, fails. It crashes down onto the floor below. The impact load of the falling slab combined with the burning vehicles overloads the floor below, which also fails. The building pancakes. This isn't disaster movie fiction. It is a very real engineering probability based on the physics of heat and gravity. We are stacking high-energy density batteries in vertical columns without adequate thermal barriers between them. The electric vehicle revolution is here, and it is vital for a sustainable future. But technology does not exist in a vacuum. It exists in the built environment. We have rushed to adopt the technology of the future while relying on the infrastructure of the past. The mega defect isn't the electric car itself. It is our failure to adapt the world around it. Until we upgrade our building codes, retrofit our parking structures with advanced fire suppression capable of cooling batteries, and acknowledge the unique physics of this new fuel source, we are playing a dangerous game of probability. We are parking the future in the past, and eventually the structural integrity of that past will give way. Does your local parking garage look ready for a 5,000-degree fire? Do you think building codes are keeping up with EV technology? Share your thoughts and concerns in the comments below. If this deep dive into the hidden risks of infrastructure sparked your interest, hit that like button, share this video, and make sure to subscribe to Mega Defect for more investigations into the systems that fail us.